Welcome everybody. We continue with second week of the calculus mathematics course, and now we start with set of objects. Where is it? Yeah, set of objects. Example, what can we say for this? Set of base 10 digits. You know, in the set, we have 0 to 9. These are 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yeah, it's easy. These are braces, or we can say set brackets. It's important, I said before, to know the information about these things in English also. You see, it's a finite set. It's a finite set. That is, we have enough number of elements in this set. Yes, next one. We can say, we can give an example, set of 26 English letters. So you see, it's starting with A, B, C, and these are dots, and X, Y, Z. So these are called dots or ellipses. This is also a finite set. We have here 26 letters, 26 elements. So we start with sets of objects. So next one. Another example. Set of even numbers. You see, here we have 2, 4, 6, 8, 10, and ellipses, dots. So this is an infinite set. This goes to infinity. So it's starting with 2, 4, 6, but it goes to infinity. So you understand that this is infinite set. Finite set, infinite set. You have to know the meaning of this. Next one, another example. You know, this one is positive even numbers. You know, positive even numbers is 2, 4, 6, 8, whatever dots, ellipses. And this set, 2, 4, 6, is a subset of, let's say here, let's plus 2n, subset of set 2n plus, or it's a subset of, you may write here 2, 4, 6, 8, and that's, you see, I think. Also, you can show the set like that. This is a big set, our big set, and subset is like that. This one is subset. Subset. Let's say here A, and let's say here B. This is B, and this one is A. Subset is here. Now another another page. Let's go with natural numbers. Natural numbers. We show natural numbers with n, and it's starting with 1, 2, 3, 4, 5, whatever, and we show n and general one, and that's here. Mostly we use n for natural numbers. You see, these all numbers given in the nature, so we use natural number term for 1, 2, 3, such as we have 1 apple, 3 kids, 5 pillows, 11 whatever, 11 football players. These are given, so we use natural numbers for these numbers. Another one. Do you know what is prime number? Yeah. Prime number follows. Prime numbers. Yeah, mostly we use prime numbers for defining atoms. You know, in chemistry maybe you said this one. We can give a definition for this one. Definition for prime numbers. P is prime if P is greater than 1 and P is divisible only by 1 and P. This is important, by 1 and P. So what are the prime numbers? You see it's starting with 2, 3, 5, 7. Is 9 a prime number? 9? No, because it's divisible by 3. You see, 9 is not prime number because it is divisible by 3. So 11, then 13, 17. It goes like that. That's, or ellipses, whatever. So these are all odd numbers, but the only one even number is, even prime number is 2. These are all odd. Okay, let's go another thing. We continue with this one. Fundamental theorem of arithmetic. Fundamental theorem of arithmetic. What's this? What's this definition? Any natural number can be factored uniquely. This is important. Uniquely, except for the order of factors. it is uniquely, but the order may change into a product of prime powers. Prime powers. Let's read again. A natural number can be factored uniquely except for the order of factors into a product of prime powers. This is important. So let's give an example for this one, such as 12 is equal to 3 times 4. So we can write it as 3 times 2 to the power 2, or we can write this order like that, but this is unique. This is also same, but in the definition, what we can say, except for the order of factors. The order change, but it is uniquely defined. So maybe another one, 70 is equal to 2, 5, 7. You know, we can find like that. 70 is divided by 2, and we find 35, and we divide 35 by 5, so we find 7, and then 7, it's 1. So we find this 2, 5, and 7 from here. Yeah. You can also find maybe 121. You know, it is 11 times 11, so 11 to the power 2. It goes like that. Yeah. Yeah, this is easy, I think. Factoring numbers is not so hard. So we can say that if it is a big one, maybe it's hard, but factoring numbers may be hard only by observing. This is important. So we have to use this one for this one. Okay, let's look another one. Yeah, we now see set of objects, natural numbers. We see set of objects, natural numbers, and what we see here, prime numbers here, prime numbers. And we saw under set of objects subset term, and another one integers. Yeah, integers. Now, next one I write here, integers. Here we show integers by z. So where can we find the integers? By the way, why do we use z for integers? In German term, Zahlen means numbers. So this is come from German. Okay, maybe you know German or you see Deutsch. Yeah. To find the integers, I mean, we can think a equation like that. X plus 1 is equal to 1. So we need to solve this equation. X is must be equal to 0. So 0, something under a number, but I don't know this one is a natural number or another one. So 0 is under some word. So another equation maybe. We find this one. I write again. X plus 1 is equal to 1. So we need 0. I wrote it. So another one, to solve x plus 1 is equal to 0. So we need to solve this equation. We need what? X is equal to minus 1. Minus 1. So 0 and minus 1 we find. So these things in integers. So we are going to find a new set that we set. This is minus infinity and coming up to 0, minus 3, minus 2, minus 1, 0, and we also know the others, 1, 2, 3, 4, and dots, and plus infinity. So we can write these things like that also, 0, plus minus 1, plus minus 2, plus minus 3, and dots. This is a compact also set, and let's look another page. Now we have rational numbers. What are the rational numbers? Also, we defined rational numbers by Q. We have P over Q. The sets is like that. P over Q such that P and Q are integers, I mean in Z, and Q is different from 0. This writing can be said as fraction or ratio. So let's go another one. This is definition part for rational numbers. Examples, you may easily understand that 1 over 2, 3 over 4, 5 over 7, maybe 109, 1903 over 2000, maybe. These are all rational numbers. There's an important note here. All natural numbers is in rational numbers. All natural numbers is in rational numbers, and all integers is in Q, also rational numbers. Why? Since n over 1 is equal to 1. This is an rational number, and this is, natural number. Natural number. So these are all, such as 5, example. 5 is an element of natural number, but we can write it as 5 over 1, so it's an element of rational number. It's easy, I think. You all know these things from your high schools, colleges, or whatever. But this is a remembering course, so we know that you know lots of things, but we have to reteach maybe again the things you know. So there's a warning here. Warning. What's warning? Division by 0 is undefined. This is important. The division by 0 is undefined. Why this is like that? Suppose or assume, what do you want to use? Assume 1 over 0 is taken to be a number. Taken to be a number. Let's assume like that. So what can we consider? Okay, let's look. Then consider some of things we know, such as 0 times 1 over 0. This is a known number, we said. We suppose that like that. So this is 0, since 0 times something x is equal to 0. We know this one. So 0 times 1 over 0 is equal to also 1. Why? We can say since x times 1 over x, we can divide each other, so it equals 1. So this is also true. So this is an one equation is equal to two things. So this is a contradiction. You also have to know this term, contradiction. Okay. So what we can say finally, so 1 over 0 cannot be defined. Okay? Cannot be defined. So another thing, some operations may be on rational numbers, some operations on natural numbers, some operations on natural numbers, such as a over b times c over d is equal to ac over bd. It is easy, you see. And division part, let's look division part, a over b over c over d. You use a over b as itself and multiply it d over c. So you turn it, flip it this one over, flip it over. What we mean, reciprocal of c over d is d over c. Yeah, d over c is the reciprocal of c over d. So we use this one, then multiply it again, ad over bc. It's also easy one. So let's look for the addition and subtraction, maybe addition and subtraction one. A over b plus minus c over d is equal to, it's easy to find this part, so you may say we find the denomination by writing here d and writing here b. So we find AD plus minus CB. So there's a common denomination here. Common denomination. What's that? Common denomination. So you easily find the solution also. Let's give some example. 2 over 5 over 3 over 8 is equal to 2 over 5, and multiply it by reciprocal of 3 over 8 is 8 over 3. So we find 16 over 15. It's easy, really. Yeah. And maybe we have like this example, such as 4 over 6. So we have both the same multiplicator here. What I mean, 2 multiplied by 2 and 3 multiplied by 2. So you may here cancel these ones and you got 2 over 3. It's a nice thing for mathematics. What do we do here? We put into lowest terms. We put into lowest terms. It's better to understand or better to solve the equations. So we are trying to put into the lowest terms, so we find the solution easily. And final note for these things, another note, such as do not use mixed numbers. What I mean by mixed numbers? Notation like 3 1 over 4 maybe, or maybe 5 1 over 2, because 3 1 over 4 means it is 3 plus 1 over 4. So it maybe you are trying to find this one that multiply this one, or we don't know what you mean, so try to use this one. Okay, now let's continue another one. Now after rational numbers we have new set of numbers. These are irrationals, maybe irrational numbers. And again, as we find integers, we try to give an equation and then find the integers. So again, we try to find the irrationals. To solve this equation, x squared is equal to 2. Let's find x here. We need plus minus square root 2, plus minus square root 2. So we have to add these numbers to rational numbers. We have to add these numbers to rational numbers. How can we do that? This is not possible. So what are the other irrational numbers? Let's find this. Let's give an example of this. And square root 2, square root 3, and there are lots of square root, of course. Maybe number E, maybe P, you know this P also. It's using to find the circle's area and the volume. And these are called oddballs. Okay? So, in fact, there are more than irrationals. Or maybe like this. Let's write this here. More irrationals than rationals. It's easy to understand this one. And last one may be real numbers, and we can finish the second week's lecture with real numbers, real numbers. We use R for real numbers, R, and it's equal to, this is an, of course this is not real. What does real means? You may ask this question. I wrote it in the introduction lecture. I said that it is a technical term, so everything is real, but real numbers is a technical term. So in this set we use Q and all irrationals, all irrationals. So we can also write the real line. We use geometric points, and real numbers, geometric points and real numbers. So let's write what I mean. We have a line here like that. So it's starting with 0 here in the middle, and we have 1, 2, 3, and 4, and it goes to infinity, and here -1, -2, -3, and it goes to minus infinity also. We have here an arbitrary unit here. I choose is like that. So you can find, and also we can say this 0 as origin, and anywhere like that. So we have such as here 3/2, or maybe here, square root of 2 is equal to 1/4, and square root of 3 approximately is 1/7. So maybe here is square root 3 and square root 2 maybe. And we also have maybe like here minus 8/7, maybe here like that. So we have lots of points in real line and on real numbers. So as right, we are going as right. What's happening? Right, increasing, and as we are going to the left, you see left, it is decreasing. So finally, here this is the end of the second week's lecture. If you want to ask any question, I wrote it again. If you want to ask any question, I will answer these on Friday online lecture. Okay, this is the end of the lecture. See you on the next offline lecture and online lecture. See you. Bye bye.